All right, so now we're going to move on to another topic called oops, it's so big. The so-called eigenvalue problem. Let's try again. Okay, so the setting is we have a matrix size n by n. And this time, we're restricting to a square matrix, as you can see. Okay, and let's make some definition. A scalar lambda is called an eigenvalue of A if this equation AX equals to lambda X has a non-zero solution X in Rn. And I need to emphasize that it has to be non-zero. It has to be non-zero solution because this equation here has x equal to 0 as a solution always. But if for some lambda it has a non-zero solution, then that lambda is called an eigenvalue of A. Such a solution, solution X is called an eigenvector of A with eigenvalue lambda. Now this lambda. Okay, so we've made this maybe funny looking definition. It boils down to this equation involving the matrix A. Right, so we're looking at, at this moment you can think of this equation as trying to find the directions so that doesn't get changed under the matrix A, right? AX is proportional to X, so you can sort of think of that as the same direction, or at least a flip of that direction. Now the problem that we're going to study, and will become more apparent as to why we're doing this later, is to find eigenvalues and eigenvectors of a matrix. Right, that's what we call the eigenvalue problem. Okay, so let's consider the 2x2 case. This is the simple case where everything can be made very explicit and indeed very simple. But before that, I should probably make a few deductions. So AX, so let's say this is a note. AX equals to lambda X is equivalent to the following. Ax equals to lambda I x. Right, I here is the identity matrix. Now writing it this way will allow me to say that both sides are the multiplication by a matrix to a vector. So then I can rewrite this as A minus, so AX minus lambda IX equaling 0. And I can then factor out X, and that would allow me to write this equation as A minus lambda I times X equaling 0. So by definition, A minus lambda I has A minus lambda I x equals to 0 has a non-zero solution if and only if A minus lambda I is singular. Right? That's the notion of being singular means. And one thing that we talked about before is that being singular is equivalent to A minus lambda I being not invertible. Okay. Indeed, if you look at this equation, if A minus lambda I were invertible, then this equation can only have the zero solution, right? If you just multiply the inverse to the left side on both equations, you'll get x equals to 0 as the only solution. So having non-zero solution means that the matrix A minus lambda I is not invertible. Okay, we're going to use that somewhat significantly. Okay, but in principle, so then another thing to notice, we seem to be doing something very strange with the screen here. Oh, that's why it looks so weird. Anyway, so I guess now I'll continue over here. That's why the thickness of the stroke looks so weird. I zoom in too much. If lambda is an eigenvalue of A, then to find its corresponding eigenvectors, we just need to solve the system A minus lambda I times x equals 0. And we know how to do that. We've seen how to do that. So now the question is how to find the eigenvectors, how to find the eigenvalues. It is not hard to find the eigenvectors when an eigenvalue is found. So the question is how to find eigenvalues. Okay. So for this, we will for now consider the 2x2 case, where everything can be made explicit, very explicit. So suppose our matrix is A, B, C, D, like that. And I want to consider A minus lambda I, and that is going to be A, B, C, D minus lambda 1, 0, 0, 1. So that is A minus lambda, B, C, D minus lambda. Okay. Now, we know that, as we just talked about, lambda is an eigenvalue of A if and only if A minus lambda I is singular, which is the same as saying A minus lambda I is not invertible. Now, is this latter condition of not being invertible that we have some criteria to work with, right? So, in general, let's remember we've talked briefly about this invertibility. Ability. In general, not in general, in 2x2 case only. Right? If my matrix B is of this form, R, S, T, and U, then let's let C equal to U, what is this? Minus T, wait, hold on, U minus T, minus S, R, I think, let's see. Yeah, I think this is correct. Hold on. That looks weird. Hold on. CRUS. Oh yeah, that's right. Okay, so let's see be this matrix. Okay, then BC is equal to you compute it if you compute it, you get RU minus ST here. Over here is R minus S plus RS. Over here is TU minus UT. Over here is minus ST plus RU. And of course, these two are 0. And what we're left with is RU minus ST, 0, 0, RU minus ST. So this is RU minus ST times the identity matrix. And let's see, you can check that the same thing is true for C times B. So you see that, so what does this tell us? So B is invertible if and only if Ru minus St is not equal to 0, right? If Ru and minus St is not equal to 0, then we can divide the matrix C by this number. Then the resulting matrix times B will be the identity, right? If Ru minus St is 0, then BC is equal to the 0 matrix, so B cannot be invertible. Okay, so what this means, applying this to the matrix A minus lambda I, what we get is that A minus lambda I is not invertible if and only if, well, whatever this quantity is in this case is 0, right? So this quantity is A minus lambda times D minus lambda minus BC is equal to 0. Okay, so this is an equation that we can use. Again, according to the discussion we just made, the matrix A minus lambda I is not invertible if and only if lambda satisfies this equation. Okay, so lambda is an eigenvalue of A if and only if this equation holds. A minus lambda, D minus lambda minus BC is equal to 0. And you can expand this. That gives you the following quadratic equation in lambda. Lambda square minus A plus D lambda plus AD minus BC equals to 0. Okay. So now this is particular. So this is a quadratic equation in lambda. We can solve this. This can be solved by quadratic formula. Right. So we now have a complete control over finding eigenvalues of a 2x2 matrix. And once we find an eigenvalue, we know how to find the corresponding eigenvectors. So that's not difficult at all. Now let's look at some example. In fact, just one example. So let's say A is like that. And I want to find its eigenvalue and eigenvectors. Okay, so for this, I want to write this equation. And if, let's say I don't remember this equation, then I just consider first of all A minus lambda I, 5 minus lambda minus 2, 6 minus 2 minus lambda. Now, so the equation we need is therefore 5 minus lambda minus 2 minus lambda minus 6 times minus 2 equal to 0. Okay, this is the equation for eigenvalues. And so we have to compute this. So it's lambda square minus well, it's 3 lambda plus here, so it's negative 10 minus negative 12, so 2. Okay. Now this equation is easy to solve. You don't even need quadratic formula. You can just eyeball the answer because the polynomial here factors as the product of lambda minus 2 and lambda minus 1. So you get 2 eigenvalues, lambda equals to 1 and 2. Now, for lambda equals to 1, you would have, you want to consider the system a minus lambda I x equals to 0, right? When lambda is 1, a minus lambda I is 4, 6, minus 2, minus 3, x1, x2 equal to 0. You can solve this certainly. Let's see here. I mean, this one is, oops. Yes, no, it's fine. So the equations in this system are 4x1 minus 2x2 equal to 0, 6x1 minus 3x2 equal to 0. And you see both, if you divide if you divide the first equation by 2, divide the second equation by 3, okay, you get the same equation. 2x1 equals x2, 2x1 equals x2. So this is just telling you that the solutions are immediately readable. x1, x2 is just x1 is x1, x2 is 2x1. So this is x1 times the vector 1, 2. Okay. So what we now see, these guys are all the eigenvectors. With eigenvalue 1. Okay. Now for the other eigenvector, so for the other eigenvalue lambda equals to 2, we still have to consider a minus lambda I equals x equals to 0. And this time the system reads, so lambda is 2, so that's 3, 6, negative 2, negative 4, x1, x2 equals to 0, 0. And once again, you can just write out the equations. It's 3x1 minus 2x2 equal to 0. And the second equation is clearly just double the first equation. So from here, you don't even need to work. You just immediately solve the equation. You immediately solve the system x1 is 2/3 x2. x2 is still x2. So the in vector form, x1, x2 is, x1 is 2/3 of x2. x2 is x2. So this is x2 times 2/3 1. And these are all the eigenvectors eigenvectors with eigenvalue 2. Okay. So this example shows you how things can work in general. So now, well, in 2x2 case, now the question is, as we've talked about, the issue, in finding eigenvalues, the issue is to determine when a minus lambda I is invertible or not invertible. And we know how to do this in 2x2 case. The question is how to determine whether or if a minus lambda I is invertible or not for bigger for beyond 2x2 case. Okay. In 2x2 case, we have this nice description of the inverse, and that leads to this quantity, and it immediately tells us, immediately gives a way to decide whether a matrix is 2x2 matrix is invertible or not. And in order to proceed to deal with the general case, we're going to need the notion, some notion. That's the answer to this question. The answer is what we call the determinant. Okay. And let's begin with defining the determinants and spend some time on this. So suppose A is 2x2. Okay. The determinant of A, that of A is defined to be that A equals to A11, A22 minus A12, A21. Okay. So I'm just defining a quantity. First of all, you notice that in case of, in the previous discussion, we have ISTU. Right. For this matrix, the determinant is RU minus ST, which is the quantity that we considered before, as you can see here. Right. If this is ISTU, then RU minus ST is the quantity that we considered before, which is the now we call the determinant. Okay. So example, and this is a very simple thing. The determinant of, I mean, if you have a if you have a 2x2 matrix, to compute its determinant, all you have to do is multiply across like these. So 2 times 6 minus 3 times 4, which is 0. Right? Okay. So now, so far we haven't done anything new. We just gave a name to some quantity that we used in 2x2 case. Now, let's consider 3x3 case. A11, A12, A13, A21, A22, A23, A31, A32, A33. Okay. Now the determinant of A is defined as follows. You take A11 and the determinant of let's see, this guy, A22, A32, A23, A33, then you minus A12, determinant of A21, A31, A23, A33, then you add A13, determinant of A21, A31, A22, A32, okay? And let's first of all see how this is constructed. Here we go. So we have A11 here, that's here. And I'm multiplying A11 by the determinant of some 2 by 2 matrix. And that 2 by 2 matrix is here. Okay. It's the 2 by 2 matrix you get by deleting the column and the row containing A11. Okay. This one. Now then you move on to A12, keep in mind there's a sign. A12 is here. Now you multiply A12 by the determinant of some matrix. Where is that matrix? Again, that matrix is formed by deleting the column and the row containing A12. What's left are here. A21, A31, A23, A33. Okay, and finally, we have plus A13. A13 is here. And we multiply that by the determinant of some 2 by 2 matrix. Again, the 2 by 2 matrix is formed by deleting the column and the row containing A13. So that will be, oops, I don't mean to erase it all. A21, A31. So that will give us this one. Right, A21, A31, A22, A32. Okay, like that. So this is some definition that makes some sense. Let's look at some examples. Or maybe just one example. Yes. Let's make it easy for me. So 1, 5 minus 2, 2, 3, 0, minus 1, 4, 1. Determinant of A is then, well, what's the rule? 1 times the determinant of 3, 0, 4, 1 minus, keep in mind there's a sign here, minus 2 times the determinant of 5 minus 2, 4, 1 plus negative 1 times the determinant of 5 minus 2, 3, 0. Okay, and that is equal to 1 times, this is 3 minus 2 times, this is 5 minus negative 8, right? So 5 plus 8, and then minus 5 minus negative 6, so plus 6. So minus 6. Okay, so it's 3 minus 26 minus 6. That's 32. 3 minus 32, negative 29. Okay. All right. So naturally you wonder, how about 4 by 4, 5 by 5, and so on. So for this, we're gonna make a definition in general, but it's gonna be an inductive definition. Now that we've defined determinants for 2 by 2 matrices and 3 by 3 matrices, we're gonna use this definition. So we're gonna in the definition of 2 by determinant for 4 by 4 matrices, we're gonna use that. We're gonna use determinants for 3 by 3. In the definition for determinants for 5 by 5 matrices, we're going to use determinants for 4 by 4 matrices, and so on. And we have to sort of formalize this as follows. We need a definition here. So suppose A equals Aij is an m by m matrix. Okay. So define. Oops. Yeah, no, it's fine. Define MRS to be the m minus 1 by m minus 1 matrix obtained from A by deleting the r's row and the s column. Okay, so you can see this in picture, say like this: A11, A12, A1s, A1n, A21, A22, A2s, A2n, AR1, AR2, ARS, ARN, AN1, AN2, ANS, ANN. So this is A. Now if you're looking at the rth row here, delete it. Looking at S column here, delete it, and squeeze everything back into so that there's no space left. You're gonna get m minus 1 by m minus 1 matrix. That's what we call the MRS. Okay. All right. And there are quite a few that you can form. So for example, if I have my A being this bit complicated 4 by 4 matrix, okay, and let's try to find M21. Okay, how do I find M21? I'm supposed to delete second row, so here, first column, so here. What's left is whatever that's not highlighted Okay, so this is M21. Now, I don't know, let's do one couple more example. M23. Now this is gonna be not so easy. So for M23, I still want the second row out, but now I want to keep the first column. I want the third column out. Okay, I want the third column out. So this one is out. So that's left with 1, 2, 3, 4, 2, minus 1. I think that's minus 2, 3, 1. Okay, and you get the idea. Let's try one more. M42. For M42, you want the fourth row out here and the second column out there. And now what's left is 1, 0, 4, 1, 2, 0, 3, 0, minus 1. Okay, things like that. Okay, and now back to 3 by 3. Now with this notion, oh, I forgot the name, MRS here, this is called RS minor matrix. RS minor matrix of A. Okay, now with this notion of minor matrices defined, we can rewrite the definition of determinants for 3 by 3 matrices as follows. Okay, again, this is 3 by 3 matrix. So the determinant of A, as we have defined, is A11 times the determinant of, right, what was it? It was going to be this 2 by 2 matrix obtained by deleting the column and row containing A11. So that's exactly what we call M11 minus A12, determinant of M12, right? Again, this is obtained by deleting the column and row containing A12, and plus A13, determinant M13. Okay, very good. So now let's make the following observation. Let's introduce a sign. Right, there's something about this sign here that's a bit annoying, and we can make these into we can sort of formulate a convention that includes the sign so that you don't need to remember it, right? As follows. Okay, just notice that minus 1 raised to the 1 plus 1 power is 1. 1 plus 2 power, that'll give you minus 1, which is the sign. Minus 1 plus 3 power, that's again giving you a 1, which is the correct answer. And the point of this convention is that 1 plus 1 is this 1 plus that 1. 1 plus 2 is this 1 plus that 2. And 1 plus 3 is this 1 plus that 3. So this really is now a way to remember the sign by just, if you use the indices of the entries to recall the signs. So that's very good. Certainly seems useful. And for this, there's a definition that we can make. Going back here, when we have in general n by n matrix, we can form MRS, the RS minor, the side minor, RS side minor, or cofactor, of A is just this expression, minus 1 raised to the R plus S power times determinant of MRS. Okay? And we sometimes denote this by ARS. Okay. Okay. So now there is another thing to check. There's another thing you can ask. Right? Notice that in this description or definition of the determinant of our 3 by 3 matrix A, we move along the first row, right? Because that's A11, A1. We get the expansion is given as A11 times something minus A12 times something plus A13 times something. So this could be called an expansion along the first row. Now, there's nothing really special, as it shouldn't be, about the first row. So what if you write down the expansion along the second row? That would be the following. There's a sign convention, minus 1 or 2 plus 1, A21, that M21 plus minus 22, 2 plus 2, A22, that M22 plus minus 1, 2 plus 3, A23, that M23, right? There's also the third expansion along the third row that you can consider. Expansion along the row. That would be minus 1, 3 plus 1, A31, that M31, plus minus 1, 3 plus 2, A32, A32, that M32, plus minus 1, 3 plus 3, A33, that M33. Okay. So, but we've decided that we decided to call the expansion of the expansion along the first row the determinant of A seems to be some intrinsic quantity associated to A. But what about expansion along the second row? What about expansion along the third row? We'll discuss this further, but before we do this in general, we should look at an example. Let's see, where is it? Yeah, this one, the one that we worry about already. 1, 5 minus 2, 2, 3, 0, minus 1, 4, 0, 1. Okay, so we've worried about this already. We've computed the determinant according to definition, and that comes out to be minus 29. Okay. Oops. Yes, now let's do that. Now second expansion along the second row is computed as follows. So 5 times the determinant of, I think there's a sign here, so minus 5 times, that's 2 minus 1, 0, 1, plus 3, determinant of 1 minus 2, minus 1, 1, minus 4, that's 1, 2, minus 2, 0. This is minus 5 times 2, plus 3 times, this is 1 minus 2, negative 1, minus 4 times negative 4, so 4. So this is negative 16, negative 19, negative 29. Okay, expansion along the row can also be calculated. Now this time there's no sign in the beginning term. Minus 2, 2, 3, minus 1, 4, determinant, minus 0. And whatever this is doesn't matter, but let's just, for the sake of completeness, write it down. Like plus 1 times 1, 5, 2, 3. And that is minus 2, 8 plus 3, 11. The second term is 0. So plus 1 times, what is this? 3 minus 10, negative 7. So negative 22 minus 7, negative 29. Negative 29. And as you can see, all three expansions produces the same answer. And this is not a coincidence. In fact, this is a general phenomenon that we will not prove, that expansions along this type of expansion along any row will give you the same answer for any matrix. And for this reason, it will make sense to define any of this expansion as a specific number, as some number intrinsic to the matrix A. Okay, and we will talk about this more in the next lecture.